Okay. Hi, I'm Russ Altman. I'm one of the associate directors at HAI, and I'm really pleased to introduce today's speaker, Sheng Wang. I've known Sheng for quite a while. He was a postdoctoral fellow in my lab, where he made several incredibly innovative and creative solutions in the area of mostly bioinformatics. And he changed the direction of our lab in many ways because the students were paying attention to what he was doing and picked up much of his work, and you'll see it scattered throughout all the PhDs that have been awarded since he left. So before that, he did a PhD in computer science at the University of Illinois at Urbana-Champaign. He had a BS in computer science from Peking University. And now he's an assistant professor at the University of Washington, where his work has continued and, as you'll see, really exploded. The work he did with us was in zero-shot learning, and which is very important in biology because even though we think we have a lot of data, compared to some of the big tech applications that have huge amounts of text, huge amounts of images, our data is very limited. And so that is always a struggle. And I think he will address some of those things even today. So we're really glad to have him. And I think there'll be a Q&A afterwards. I think there will be a live Q&A as well as the Slido deal if you're remote. And we will try to do honor to all ways of asking questions. So without any further ado, welcome to Sheng. Thank you.
Thank you so much for the introduction. So can everyone hear me clearly? Okay, great. So as Russ mentioned, I was a postdoc here working in Russ lab from 2019 to 2021. And actually at that time, we were also working on generative AI. It was not called generative AI at that time, it's called contextual word embedding. It was a model called BERT. And we found that that model works very well on modeling biomedical text, like clinical notes, scientific literature. But these days, generative AI has been applied to way more modalities, like biomedical images, or single-cell gene expression data, protein sequence. So today we are going to talk about new medical applications that cannot be addressed by traditional AI models, but now can be solved using generative AI approaches. So first of all, I would like to give a brief review of 4 different stages of 4 different paradigms of AI in medicine. The first one is very well known, deep learning. It's very effective. But the problem with deep learning is that it's very time consuming, and we often need to develop different models for different applications, even if we are modeling the same kinds of input. And then we cannot effectively leverage the data across different tasks. And then since 2022, people have this very nice idea of building a foundation model where we use one model to solve many different tasks. And in this way, the data from different tasks, different applications can be used by the same model. So ChatGPT is one of the most successful foundation model. Since last year, people start to explore the idea of multi-modal foundation model. So this time, not only in the output space, we can have different applications, even in the input space, we can consider multiple kinds of input. Like we can consider pathology image, MRI image, genomics data, using all of them for cancer research. And this year, there's a new trend of multi-agent model, where multiple foundation models collaborate, discuss with each other, and one foundation model might be responsible for modeling genomics data, another foundation model might modeling pathology data, another foundation model might be responsible for modeling MRI data. So they work together to tackle a medical case together. This is like a simulation of something like molecular tumor board, where we have different types of doctors, pathologists, radiologists, and they work together to solve a very challenging medical case. Today, I'm going to focus on the third paradigm, multi-modal foundation model. So the reason we want to study multi-modal foundation model in medicine is because medicine is inherently multimodal. There are lots of complicated diseases like cancer, hypertension, diabetes, or even COVID. They are very complicated diseases that we will see signals all over the human body. It's not about a certain organ or just a few organs. For example, diabetes, we can see issues in teeth, in retina, in brain, in heart, and then we will need medical tests all over the body. Okay, we need something to measure the heart, measure the teeth. And those are kind of medical images. There are so many different medical images. They cannot simply be modeled by the same kind of computer vision methods because they are inherently very different. Some of the medical images are 3D images, like MRI, CT. Some are 2D images. Some images are very large. It needs a high-resolution view, like pathology images. So those images need to model differently. And if we further consider like genomics data, clinical text, there will be many different modalities. So we need a comprehensive framework to consider all those modalities to model this kind of complicated diseases. So today I'm going to talk about 3 recent work from my lab covering those kind of aspects. The first will be a pathology foundation model, where we try to model very large pathology images. The second work will be a 3D medical image model that can be used to model different kinds of 3D images. Finally, I'm going to talk about a multi-modal foundation model that can integrate and consider 9 different medical images, like MRI, CT, pathology. 9 different image types can be considered by the same multimodal model. Okay, so first of all, let's start from the pathology foundation model. Pathology images could be the most difficult one for AI models to model because it's too large. So this is a pathology image, right? It looks very small. You can put it on a finger. But if we want to see the detailed cell structure, the organization, we need to do a 20 or 40 magnification. Then this image becomes 100,000 by 100,000 pixels. So what does this mean? If I print this 100,000 by 100,000 pixel using a certain resolution, like we can see with naked eye, this small image, like a finger size, can cover an entire tennis court. So it's very large, just this one image. And then in comparison, those are the images that exist in AI model, GPU architecture. They are often used to handle, like animal classification, image classification, dog cat images. They are very small, 256 by 256 pixels. If we print them, it will be as large as a tennis ball. So this is a mismatch here. Existing AI model, GPU architecture are developed it to handle this kind of very small images like a tennis ball. But now we want to apply it to model very large images as large as a tennis court. So this scale problem has been a problem blocking the field of AI for pathology for many years. But we found that actually the solution and also the challenge here are very similar to the solution and challenge behind ChatGPT. They seem to be 2 very irrelevant domains, right? One is ChatGPT, question answering, conversation. The other is pathology, image analysis, cancer research. But the underlying challenge and solutions are the same. It's a problem called long context modeling. So ChatGPT, you might have experienced something similar. It's very good at understanding very long documents, a very long sentence. We can give ChatGPT a PDF and ask ChatGPT to summarize it. And ChatGPT can often provide a very concise summarization. And here, we want to use the similar ability to model extremely large pathology image. Our idea is to convert a very large pathology image to a very long sentence. And this sentence, the basic element is not a word or a character. The basic element here is a small image, 256 by 256 pixel that can be handled by existing deep learning image encoder. And then this long sentence will be modeled by the long context modeling techniques behind ChatGPT so that we can have an overview of the entire slide so we can predict the patient based on the entire slide. This is how we model the very large pathology image. So based on this high-level idea, we published this paper in Nature a few months ago. This is a collaboration among Microsoft Research, University of Washington, and Providence Genomics. The most exciting thing is that this model has got about 200,000 downloads per month from Hugging Face. And we are super excited to see that lots of the downloads are from countries and areas where traditionally do not have a very strong training of pathologists. So everyone can use our model to analyze their pathology images. And this is the first foundation model for whole slide pathology, which means that whole slide means the model that can analyze the entire pathology image. So let's see what we learned from this model. The first thing we learn is that we can actually use one model to fit many different cancer types. So this is very different from what we know before. Like cancer is very heterogeneous. So it's good to have different models to model different cancer types or different cancer subtypes. Here we use one model trained on 30,000 patients covering 140,000 slides from 28 hospitals. And this model covers 15 cancer types. And this model, just one model, actually achieved the best performance on 25 out of 26 tasks. This is the first lesson we learned. Generative AI is very good at handling very large data set and very diverse data set so that it can be generalized to new patient population or new domain. Let's see the specific tasks we can do here. The first set of tasks is cancer subtyping. Given a pathology image, we want to predict what is the specific cancer subtype. For example, this is an image of an ovarian cancer patient. Only based on this image, we can have about 19% accuracy to classify this image into a specific cancer type. This is very useful information for determining the treatment, determining the expected survival. And we can do well on many different cancer types. And then the second set of tasks we did is biomarker prediction. Given pathology image, we can predict which specific mutation this patient might have, and among 18 different biomarkers, we can do very well on 17 out of them. This is also very important because this can instruct the target therapy we can use to treat this patient. So those are the tasks we did, but our ultimate goal is to predict treatment. We want to know, given this pathology image, whether we should suggest this patient to do radiotherapy, chemotherapy, or which kind of specific target therapy should we apply on this patient. We found that this is very challenging. Our model actually cannot do well directly, by taking this image, predict treatment. And many existing AI models also cannot do well because this task is very challenging. And lots of information missing here, the patient insurance information, whether the patient is willing to take certain kind of treatment. We don't have that in the data. So it's a very complicated task. And then we use this second idea from generative AI to solve this problem, an idea called chain of thought. Chain of thought is a very creative idea which decomposes a very complicated task into many small subtasks. For example, here I have a showing example of a math question. It seems to be very trivial to human, right? But it's actually a very challenging problem to language model, to generative AI model, where we want to count how many tennis balls are there. And if we ask this question directly to the foundation model, to the generative AI model, the model cannot give the correct answer. If we show the process, how to think about this problem, show the details to do it, actually now, the same model, same question, the model can answer this question correctly. So this is a chain of thought. The problem is, how could we do chain of thought in medicine? How could we create such a chain here? Our solution to this is to use clinical guideline to support the chain of thought. This is a clinical guideline from NCCN. The best oncologists, cancer experts sit together and derive such guideline that given pathology image, we should first determine subtype, and after we know subtype, we should determine biomarker. After we know biomarker, then it should be a certain kind of treatment. So this is a clinical guideline derived by experts. Then we incorporate our GenAI model with this guideline and treat this guideline as the chain of thought. We do not predict treatment directly. We ask the model to follow the guideline, predict each sub-step, determine where we should go in each branch, what's the subtype, what's the biomarker, and then finally reach the final treatment. This can make the model much more accurate in predicting the treatment. And this could be a very nice way for human AI collaboration, right? So in this way, AI model will not replace the human experts. It will be a collaboration mode where experts, clinical experts, derive the guideline, and then the AI model will make decision on each branch. And I think this could be a future, have a good future implication where AI model will be like a clinical lab test, like a blood test or MRI exam, CT exam, where doctors can order. They can order a model to do something, and then based on the model output, they can do a better diagnosis. So this is the first part about the AI model for generative AI model for pathology. We cover 3 different things: the chain of thought to incorporate clinical guideline, and also using long context modeling to model very large pathology image, and also use one model to cover different cancer types. Those are all ideas from generative AI. Next, I'm going to talk about a 3D medical imaging model specifically for retinal imaging. 3D imaging is actually very important in medicine, and also very time-consuming to analyze because there could be many slices, and the disease region, the pattern might only be in one slice with a very small region. And actually, the general domain computer vision model cannot do well in 3D imaging because those models are often trained and developed on internet image or ImageNet, which are inherently 2D. So that's the gap here. I would like to show an example to further motivate the goal of developing a 3D medical image model. This is a patient, a real patient with age-related macular degeneration, and then we would like to take the OCT image, this is a 3D OCT image measuring the retina of this patient, and this image has more than 60 slides. Okay, then so doctors need to see each slide one by one, and in many of the slides, we didn't see any pattern of this disease. Only in one slide, and in a very small region, we can see disease pattern. So 2D model is very likely to overlook this kind of disease pattern. We would like to have a 3D model to consider the entire volume. Based on this, we develop a generative AI framework for modeling 3D medical imaging. The key idea here is very similar to what we did in pathology. We also convert a 3D volume to a long sentence of small cubes, and each cube can be handled efficiently by existing deep learning model. And then this long sentence will be handled by long context modeling techniques. So specifically, we use mask autoencoder to learn this kind of image encoder by masking some of the cubes in the entire volumes and try to reconstruct it. We also use a technique called flash attention to help us further ease the computation, because this is very time-consuming, very expensive to model the entire 3D volume. Based on this, we trained the first 3D OCT foundation model using 26,000 patient data. And this model can do very well on 29 different tasks, including many different retinal diseases, 8 different retinal diseases, and also many different systematic diseases. So using the retinal image, we can predict hypertension, diabetes, and many other diseases. Beyond the predicting accuracy, like what we showed in pathology and in the previous slide, we can also provide interpretation. So given a 3D volume, we can tell the doctor which slide, which region they should take a closer look. Here I show an example. Again, a patient with age-related macular degeneration. This is this patient's OCT slides from slides 18, 22, 26 to 42, so from lower layer to up layer. And first of all, this is an interpretation of 2D model. Here, the red pixels are the regions that 2D models think is very important. And we can see that 2D model often provide, the interpretation provided 2D model may not be reasonable in many slides. Like in slide 26, lots of interpretation fall out of the retinal region. And this is the interpretation by our 3D model. We can see that this kind of interpretation can make more sense. Most of the interpretation fall within the retinal region. We also see a very good consistency between the interpretation of nearby slides. For example, slides 22 and slides 26, they are very close to each other, and the region we think are important is also look similar. So this is beyond a very accurate prediction. In addition to predict that this patient has AMD, we can also tell the doctor what region they should take a closer look, so doctor can have a better understanding of the model. And then we also found that 3D model using generative AI techniques is better at generalization. So our model is trained on patients from UW Medicine, University of Washington Medicine, and then we test this model on 4 other centers, and all show better performance compared to the 2D model. Another very interesting for generalization is cross-device generalization. Those are 2 images, right? They look very different, but they are actually from the same patient, same eye, but screened by 2 different devices. So they look very different shape, very different angle, but they are actually for the same patient, same eye. And then if a model is trained within all the patients from the same device, and then we apply this model to a second device, the performance could be very bad. But we found that our 3D model, OCTCube, which is trained on all images collected from the first device, actually can do very well on images from the second device. It's actually better than the 2D model, which is trained and test both on the second kind of device. This is because the 3D model will focus more on the disease region rather than the entire shape or the angle of those kind of specific image. So it will have a stronger generalization ability. Finally, we also do systematic disease prediction. Given a 3D image, we can now predict other diseases like diabetes, hypertension, many other diseases. Here, I would like to give a case study of a 3D model, how a 3D model successfully detects the diabetes. This is a real patient, the retinal, okay? During the first visit, the 2D model did not identify that this patient has diabetes. But our 3D model successfully detects that this patient has diabetes and also highlights those regions that might indicate diabetes and provide doctors those regions to do a closer look. And then after 1 year follow-up, there are more signals on many different slices. And the 2D model also successfully detected diabetes. But our 3D model actually did this 1 year earlier. So this is the second part of my talk. We talk about 3D medical imaging, and we show that 3D medical imaging is very good at generalization to new population, new device, and even other diseases. And we also show that 3D model can provide a more consistent interpretation across different slices. This is much better than the 2D model in terms of interpretation. Next, I'm going to talk about a new model, which we integrate 9 different kinds of imaging modality. In our pathology work and also in our retinal work, we also did some multi-modality analysis. In pathology, we model both medical report and pathology image. In our OCT work, we model 2 kinds of retinal images, OCT and IR image. But I should say that they are still limited because the information here between these 2 modalities are very redundant. Medical report is like a description of the image. And these 2 kinds of images are like 2 different views of the same eye. What we want to do is have a model that can consider all kinds of images, and then we can have a better understanding of those kind of systematic disease that have signal everywhere. But this is very challenging because the existing AI model framework is a state-of-the-art framework called CLIP that is limited to only 2 modalities. Then how can we have a generative framework to modeling 9 different image modalities? Our idea to do this is inspired by a constructed language called Esperanto. So if you know Esperanto, you know if everyone can speak Esperanto, and then we do not need any translator between any 2 persons, right? We can translate everything to Esperanto and then communicate in Esperanto. We think this is a very nice idea to integrate different medical images. If we have foundation model for every single medical image modality, like one for MRI, one for CT, one for pathology, then we can integrate all of them by projecting all of them to some Esperanto in medicine. So the question is, what will be the Esperanto in medicine? And our idea, this is a new paper we just published, is to use human language as Esperanto for integrating different kinds of medical images. Those are 9 very different medical images we want to integrate. CT, MRI, pathology, ultrasound, they are very different. Some are 3D, some are 2D, some are large, some are small. But there's one common thing. Every medical image has a medical report. So there's always a text data associated with every medical image. Then we can use text data to convert or to project every medical image into this shared space, a text space. Every medical image will be projected to text space using the associated medical report, the text data. And then in this space, text space, 2 images will be similar, not because they are the same modality, not because they are both pathology image. A pathology image could be similar to another CT image if they are describing very similar cancer patients. So we can capture the underlying semantic information using this text space. To build this projection, we use 7 million images from 9 different image modalities and then project everything to the text space. We have lots of quantitative evaluation in our paper, which you can take a look later. We have tried segmentation, object detection, many different things. But here, I would like to show what we actually deliver to the doctor, the tool we built. We are pursuing this high-level idea to do something called GitHub free. We hope the doctors will not like download the code from GitHub and write their own code to do application. They can use the web server tool. This is a tool we built. You can think this as a Google search engine where user can upload an image and then type anything here to communicate with this image. Here, for example, the user wants to know what might be the long nodule in that chest CT, and then we can simply search for long nodule in that chest CT. In free text, there's no control vocabulary, there's no fixed vocabulary. You can search for anything like in Google search engine. And then our model will find that long nodule, segment it, and also label it. Tell the user where the long nodule is. And sometimes maybe we do not have lots of experience with medical images. I want to find all cell types from this pathology image. I don't know what's the specific cell type here. Then I can simply search for get all cell types And then the model will be able to find all 3 different cell types, label them, segment them, and tell the user what might be the cell types here. So this is like a search engine where you can freely text anything and then to analyze your image. And this has been applied to 9 different images we collected in our data set. And it's also very fast. Here I show an example. So this is a pathologist's annotation of a pathology image. The pathologist needs to label, circle every cells, label them, color them. And you can imagine this is very time-consuming because there's more than 300 cells here. But our model can automatically find everything by simply being asked like get all cell types. And we can get all the 3 cell types, label, circle them, and has a more than 19% consistency with the pathology annotation. So this is what we did using some public data set. Now we are building this model within UW Medicine by collaborating and collecting data from doctors from many different domains. We call it data racing in contrast to fund racing because we want to raise data from different experts, and then we can build one model, cover all those kind of medical data. And this model then can be used to study different kind of systematic disease, hypertension, diabetes, where we will see signal everywhere. So those are the 3 paradigms, those are the 3 works I would like to talk about today. Next, I would like to briefly talk about the 4th paradigm, which is something we are working on this summer. We are wrapping up some papers on this, multi-agent framework. This is what we hope to deliver to doctors. It's something like Microsoft 365, where it's a full package of everything. You can have tools to receive email, you can have tools to make slides, you can have Word, PowerPoint, everything for your daily business need. We want to also do something like this, where we will integrate lots of different tools. Some are developed by us, like foundation model, some are developed by others. We integrate all of them to support all kinds of research in cancer study. It will cover genomics, cover drug, cover image analysis, and the tools will be controlled and used by a large language model like GPT-4. And then those tools will form a multi-agent framework. And then we are applying this to something called the molecular tumor board, where lots of experts sit together, like radiologists, pathologists, sit together to study a medical case together. We will have AI models offering different things and discuss, communicate with this doctor to share and to solve this question, that medical case together. So this is what we are currently working on for the multi-agent system. So this is all about the 4 paradigm I talked about. And next, we can also think about some future work. If there could be the 5th paradigm, what that will be. Because generative AI is developing so fast, we see like breakthrough almost every month or every 2 months. What might be the next paradigm? I think first of all, we can see a trend here where we always use one model, and this model is becoming more and more powerful by doing many different things and taking different inputs. And then to think about the 5th paradigm, we can first briefly summarize this talk and think about what we learned from generative AI for medicine. The first thing we learned is that medical foundation models are very accurate. They achieve the state of art on many different things: medical question answering, conversation, image analysis, multimodality analysis. It's very effective on many different tasks. The second thing that might be less well known is that medical foundation models are very heterogeneous. So here I show the data source of 3 best pathology foundation models. One is the purple one is the one I just presented, and there are 2 other models. One is built by Harvard, one is built by Memory Sloan Kettering. So they are all very good models, and they actually show comparable performance. On some benchmark, our model may be the best. On another benchmark, the model from Harvard might be the best. So they are comparable models. But the very surprising thing is that they are actually trained on very different patient population. They don't share the training data. So our model is built mainly from patients from Washington and Oregon, and then the 2 other models are built from 2 other places. So they don't share they share the training data. So there's a good opportunity for us to do some ensemble learning here by combining them. The third lesson we learn is more striking. Less than 0.001 existing medical data is used by even the largest medical foundation model. This is in contrast to ChatGPT, OpenAI, GPT-4. They probably have used most of the human text data, right? All the books, everything on internet. GPT-4 might already have covered 19% of all the existing human text data. But in medicine, the story is totally different. Here I have some estimation. It's not very accurate because it's hard to estimate the total number of CTs of pathology. This is the best estimation. I think it's also the lower bound. In US, there's at least 18 million CT per year. But even the largest CT foundation model, the existing largest CT foundation model, is only pre-trained on 100,000 CTs, collect from 10 years, patients of 10 years. And they already achieved a state-of-the-art result. On pathology, there are more than 100 million slides per year, but even the largest model is only trained on 170,000, again, covering 10 years. So the best model, already state-of-the-art, they are only trained on less than 0.01% of data. There's a huge opportunity if we can train a model using all such data. Then this is the fifth paradigm I'm thinking about. Maybe in the future, we can build a model, I call it a world model, using one Gen AI model, using data all over the world. So there are different medical centers, right? Some in US, some in Asia, some in Europe. Every medical center can build their own foundation model. We are now going to collect data all to somewhere to one medical center. Every medical center build their own foundation model in a distributed development environment. And then we will have a mixture of experts model, a very small size, a lightweight model that integrate all those models built by different medical centers. And this will have less privacy concern because only the model weights will be shared. We are not going to share the data across different medical centers. And then what we need to build this kind of world models that collect everything, collect lots of models, thousands of models over the world. First of all, we need accessible Gen AI techniques and tools like GPUs, like streamlined pipeline, like easy to use code base. So everyone, even if they are not AI experts, can build Gen AI model on their medical data. Secondly, we need a mixture of experts techniques to integrate all those thousands of models to get one model that can learn from all these models. And we hope those models, the individual model is very small, so the mixture of expert model can integrate all of them to load all of them at the same time. And then what will we achieve if we have such world model? The first thing we can do is rare disease. A disease might be rare, very few patients in one particular medical center, but if we can collect data, collect a model all over the world, we will see lots of similar patients. This can help us treat this kind of rare disease. The second thing is systematic disease. We have so many data covering different modality, different population, and then we can better understand systematic disease that cannot be addressed using a single model. And if we can do systematic disease, there might be opportunity for drug repurposing. If we see a drug traditionally used for treat retinal on this kind of modality, now can also be applied to another modality, then there could be an opportunity for us to do drug repurposing. Finally, we can also leverage the ability of generative AI to generate invasive imaging using non-invasive imaging. This can also help. This can also be a big breakthrough in medicine. So this is all I want to talk today. And also, I would like to acknowledge all of my collaborators at UW Medicine again. And finally, I would like to say that lots of people tell me that AI is medicine like a specific subdomain of AI. But actually, I think medicine is way more than a specific subdomain of AI. Medical AI will actually prove the value of AI. Working in AI is very exciting. It's like 100 years ago, people working on theoretical physics, lots of breakthrough. But theoretical physics will show their value by building concrete things, like a very tall building, a bridge, an aircraft. I think AI also needs to show its value by looking into this kind of very important applications. And medical AI will be such application that is very important and will prove the value of AI. Finally, I would like to again acknowledge all of my collaborators, my students. I'm happy to take questions. Thank you.
Thank you. Now I am on, yes. So I think we're going to have some questions from Slido, but I would like to start out with this group. And with your permission, I'll ask first kind of technical question. In your two foundation models, you showed like breaking up the foundation model for pathology into a series of smaller images. But you need to create like an alphabet or a lexicon of words, don't you? Because every one of those is a little bit different. But doesn't the model need to like put them into classes so that it sees repeating patterns?
Yeah, so this is a very good question. In the pathology, it seems to be like counterintuitive, right, to break down a large pathology image into a sequence of small image, because it seems that we will lose the sequence, all the information. So first of all, we will have something called positional embedding.
So it's not showing, can we show the slide?
Slides here.
Thank you.
Yeah, so we will have something called positional embedding. So every small image, in addition to the image encoder we use to model it, which will know what the image looks like, we'll have also another positional embedding to tell where this image is in this giant, large image. And this pathology embedding will also tell us which two images might be more related due to their position, not what they look like. So this could be served as some kind of alphabet or some vocabulary to help us capture this kind of detailed information.
So that you do have a finite number of tokens.
Yes.
And what is the general number of tokens that you wind up working with for these kinds of images?
So generalized token could be like more than 60,000, like what NLP people also did for text domain.
Right.
The more token we have, it will be more fine-grained, more accurate.
Great. And so now we are ready for some questions. And do I bring the mic? Oh, we have a mic here. Oh, either one of us can do it. There you go. I'm closer.
I love the analogy to Esperanto, and but it immediately made me think from the point of view of Gen AI, we're ahead in text, so it's a natural Esperanto. But if you look at a repair manual for a car, the reason they turn an engine into a bunch of line drawings is that information represents the salience of the various parts, just like an anatomy does for a body, whereas radiological and other images are too dense in information, and most of it you're actually trying to throw away. You're trying to find the salience of the marker that indicates the pathology. So it strikes me that before you go global, it would be worth experimenting on whether or not the Esperanto would be something like vector or simple line drawing that's just edge detection, and turn all of those into something like that and then compare them, because text has all sorts of human biases in it that are based on the reports that were originally made. I mean, maybe the problem there is that you'd have to make synthetic data out of the line drawings, and then they're being compared instead of there being a human creating the report, but something image as the Esperanto.
Mm-hmm. Yeah, my understanding of this question is that you mean text data will have certain kind of bias or lose some information that is actually in the image, but may not be described in the text due to like doctor preference, right?
Yes.
Yeah. So first of all, during our conversion of image to text, lots of information are missed, lots of information lost, lots of like information captured in the image, but not written by doctor notes. They will be lost during this process. And then this kind of model will more like be a model for human to interact through text. If something has been asked using the text we collect here, and then if a user asks a similar thing, we will be modeled to do it accurately. If something was never written in human doctor notes, and then people ask it later, we may not be able to do it well. So that's true. Lots of information will be lost. And then in terms of human bias, we hope that by collecting lots of such data, here we have 6.8 million, it will somehow alleviate the human bias because the data from different experts, different annotators, and this will be a more unified view of how people think what we should look at, those images and those kind of data. Another important thing we did integrate dramatically here is that there's lots of clinical notes, scientific literature, text data that are not associated with image. They are also valuable. By incorporating them in later in the future, this can greatly strengthen our ability to model text. And then we might find new things for those images have never been discussed, have never been talked about by notes before. So this is what we are trying to do by collecting more text data in the future.
I have a follow-up. I do see the question, but I have a follow-up while we have this slide. Are you taking the textual summary of the entire image, or are you able to focus in that a certain area in this image corresponds to a certain area in this other image, and so you're going to text that's below the level of the entire study?
So we are not doing it at that image level. For each image, we will find different objects. So one image can generate multiple data points here at the object level, not at the image level.
Okay.
Some images are too large, some are 3D image, so we are doing it at object level. There's a segmentation process, find all the objects and then map
So if I'm understanding, you might find one red dot, which is just a subset of an MRI, but it might be close to the entire summary of an ultrasound.
Yeah, exactly. So two-person DLMI might be very different, but there might be some common part of this DLMI. Then they can also be mapped and be close to each other, and then we can connect those two patients.
Yeah, thanks for the talk. Really impressive. And can you share more? Thoughts on how to design the human-in-the-loop system so that you can make sure your AI system to be more trustworthy and transparent, because that's super important for doctors that can really use such systems in their daily work.
So right now, I think that's another very important topic of AI safety in medicine. It's not like we're explored. We're also doing lots of research in that line. And I think the AI safety issue is very important. And the two things we found is important. One is called hallucination, where we give an image and we give a question. The model actually answers something that is totally irrelevant to this image. And this is something have been less studied in multimodal setting. I gave a pathology image and asked the language model, what can you find from this CT image? But this question doesn't make sense anymore. But the model can actually still answer something about CT image based on pathology image. We are doing something to address this kind of framework. We cannot do it. But what we did is to generate lots of such valid data points, like a pathology image and a CT question. And then we force the model to say, I don't know, I refuse to answer. We generate lots of such kind of negative answers. And then to make sure that the model, knowing whether they know and don't know about this kind of question. So this is what we are doing now. And I think it's a very important thing we need to address before those models can finally be delivered to doctors and clinicians. Yeah.
Thanks.
Great.
Hi, Tony. I used to be a healthcare consultant, and my partner is actually a radiologist. So thank you so much for doing this. Several part question. One is, how is the use of synthetic data play into this, or at all? Second is, what are the weights that you're using? How do you determine the weights on the mixture of experts model? And I'll just stop there for you.
Yeah, so I think this is a very good question. For synthetic data, we actually didn't use synthetic data in any of those three frameworks or those kind of models. We tried to do it, and we found that the performance actually didn't improve by using synthetic data. And there's a recent Nature paper showing that by using synthetic data, that's not in medicine, that's in general NLP, actually hurts performance. And we have the same feeling here. Maybe it's better to use real-world data, because given there are so many medical data we haven't used, right? We only use small amount of data rather than synthetic data. And also the medical data we use collected now is relatively small compared to general domain data. Then it's very hard to generate high quality synthetic data from existing data. So that's why we choose to still use real data rather than doing data generation. And what's the second question?
Weights, the weights of the experts in the mixture of experts.
So in the mixture of expert model, right now we are doing a very standard way as the general domain AI model. It's just use some neural network at gates based on specific input. This model gets based on specific pathology image. We have another neural network to know which model, which foundation model we should apply this pathology image to. For example, in the 3 pathology foundation model I show here, they are trained from very different sources. That's one thing. They are also trained from very different cancer types. In our model, we mostly train on lung cancer, so we are doing very well on lung cancer-related tasks. And the other 2 models might doing well on other breast cancer or another cancer type. If the pathology image is lung cancer, we are likely to assign large weights using our model, small weights to other model. If the image of breast cancer, we might assign small weights to our model and large weights to another breast cancer-focused model. That's how we do it, but that will be determined by neural network, not like a manual determination.
Oh, sorry, thank you. If I can quickly follow up on that, you mentioned using data from other countries across the globe. I'm more so concerned in terms of like age, regional, race differences in terms of how that data is being fed and what the weights are going to be like.
So if we want to use model from other regions, then we need to use a mixture of experts model to do it. It could be very different population. Right? Most of the data still are collected within US. There will be bias to certain population, certain race. And then in the future, if we have a new patient, based on this patient demographic information, we need to determine how much weights we should put on model from US how much weight we should put a model from like Asia or other places. This is what we did. That's where we definitely need a very important mix of expert framework. Like what Russ mentioned many years ago, we work on zero shot, few shot. We don't have lots of training data. Now, even if in large language model, lots of data, we still face this problem. For certain population, we have a small amount of training data, then we need to have mixture experts to know which expert we should ask for this population. So that's true. That's very important.
Okay. Hi. Oh,
Go ahead.
hi. Thank you so much. Really enjoyed your talk. I'm coming from the healthcare side, and I was curious about how you have evaluated the accuracy of the scans or the pathology that you've integrated into the models. So, for example, there are a variety of reasons why we might order imaging from but a clear follow-up reason. For example, a patient has a certain condition, and you're following, for example, how the tumor burden looks pre and post treatment versus a patient that's coming in with an undifferentiated problem, and you're kind of trying to figure out what's going on. And so, based on those cases, that might affect, for example, the radiology read. And oftentimes there's a disclaimer where the radiologist is, saying, please correlate clinically. So I'm curious about how you've, decided what types or, what types of images, I suppose, you've integrated into the models, and if, and how that's kind of affected your analysis.
You mean like how, given so many data, which specific image modality of which population we were used to train the model? Is this your question?
Sort of. So I guess I'm wondering, are you just taking scans of all comers? Are, were they clearly for example, the CT scans, for example, were they a specific population with a specific medical history where there was a clear, discrete reason for why the imaging was obtained versus, you were getting CTs from the ER where maybe it was a more undifferentiated complaint?
Yeah, so this is a very good question. Actually, right now, we train a foundation model. The model is specifically developed to target this kind of question. Foundation model is just not like one model we train and that's it. It has two stages. I didn't describe it here. In the first stage, we train the model. It's like a base model foundation. Almost every data we can collect. We want it to be as diverse as possible to cover everything, all kinds of conditions. And the second stage, if I want to apply this model to this population or this kind of task, people with this kind of task, then I will further fine-tune or refine this model with limited data there. And this is what we did. In the first step, in the foundation step, we try to just use all the data we have, so this can cover everything. In the second step, based on the application we focus on, we will refine the model using the data of that population, of that kind of scan. And our model has been applied to 26 tasks when I talk about this model. You can think as a foundation model, get 26 different copies, one for each task. And those copies are similar to each other, but not the same. So if we have a new population, we will generate the 27th, another copy there, based on some limited data here. And for new population, we often need hundreds or maybe even less than 100 data to quickly adapt to that population. So this is a strategy we use.
It's interesting because the question that you asked raises the issue that the same CT might have a different report if it's, I have no idea what's wrong with this patient versus I know what kind of cancer they have, I've just given a treatment, and I want you to tell me if the patient is getting better. And those are two very different questions on the exact same CT potentially.
Yeah, those two questions will be solved by two different copies of the model.
Well, thank you very much for your talk. I think it's amazing if all of that could work and be implemented. I have two questions. The first one is about the accuracy. How do you measure how well does one perform? Do you follow up the patients? Do you have doctors reviewing everything? And the second question is, you talked about only using a very small amount of data. Why that meant that small amount? Is it technical limitations or something else?
Oh, this is a great question. So first of all, how to evaluation? All the data, we have, that's based on the doctor's diagnosis, the doctor's annotation. So for example, for pathology, the pathologists will look at those pathology images and tell us the specific subtypes. They are already stored in the database although we do a retrospective study by taking all the pathology beforehand, train a model, see whether our subtype classification match the doctor annotation after 6 months or 12 months. But they already happen in the database. For biomarker prediction, it's also the same. We have those kind of biomarker labeled by doing other kind of tests. Now we just want to see whether pathology image can do it or not. So everything is either through other kind of tests, other kind of experiments, or through doctor annotation. So this is the annotation. And for small, there's another interesting question of why do we use small amount of data to, in the second stage, to generalize to many different tasks? I think well, first of all, we often do not have so many label data. In the first stage, when we train the foundation, we do not need any label. We only need the image. We don't need to know whether this patient has cancer or not cancer, the cancer type biomarker. We don't need such information, only need image. In the second stage, we need those kind of information, cancer or not, specific biomarker. So the second stage, the data, we need annotation so we cannot collect lots of large amount of data. So that's one limitation for why it's small. But another thing, it's not like a limitation. If the data is small in the second stage, a 200 or 100 population, it will be a more fine-grained, more focused population. This is better than collecting lots of data in second stage because the population will be more noisy, more diverse. That's why, and that's the ability of generative AI. It's a strong adaptation ability to many different tasks. So we hope every task be very focused on only very few population. If the task is very general, then it may not work well for a certain patient. So that's the idea here.
Another facet of that question was when you said 0.01% of all CTs, or a very small fraction. And I think part of the question could be, is that political issues or technical or social? Why? How hard would it be to get those millions of scans that are done annually and are not available to you right now?
So you mean this
question on the lower left?
This one?
Yes.
Yeah. So this is because this is the data estimated by the entire, all the medical center in US. And in medicine, we know probably data sharing. It's impossible for all the medical centers to send data to somewhere. That's impossible. That's a limitation. But every medical center, just by using their own data, like our data is from Providence, that's enough to train a strong model.
I see. So this is part of your, this is what drives your vision for the world model.
Yeah. Because people will not be willing to share, put all data. There were lots of concern, privacy, ethics concern.
I think there was a question over here. Who had their hand up?
And then we'll make sure we get in a couple from Slido too.
Okay. We have one here and then one in the back, and then we'll go to Slido. I think we have time, don't we?
Yeah. Yeah. Hi. So you mentioned somewhere saying that one model calls the multiple models. I guess you're using the React framework to call one to many. It has a limitations of the inference speed. Do you implement anything to improve that inference, or it's there?
So are you meaning vision transformer for the one model to?
Correct.
Yeah. So this is a very good question. Pathology image, if we convert it into a long sequence like this, and so the question is that if we convert a large pathology image to a sequence of many small images, it'll become a very long sequence. And in AI, we use something called vision transformer, and that's very slow during inference time. So this is true, it's very slow. Our model is very slow during inference time. But it's often not a problem in medicine. Given pathology image, we spend like a few minutes. Slow, but still can be done in a few minutes, not in a few seconds. It's not like ChatGPT, a type of question I hope to get the answer in a few seconds. Here, I get pathology image, I can get the answer in 2 or 3 minutes. In medicine, it's often acceptable, this kind of inference speed. Not 2 or 3 seconds, but 2 or 3 minutes, that might be fine for a given patient. And in addition, we actually make it faster by using a technique I introduced here called flash attention, and also another technique we use in pathology called the long net to make it relatively faster. But the inference time is something we are not trying to prioritize. We think it's acceptable, even if it's just a few minutes.
Do you use any diffusion technology to?
We didn't do diffusion technology here, but in some other projects where we actually want to generate something. For example, we have a pathology image, and we know this patient is this kind of cancer subtype, OCS. And then sometimes doctor might ask, what this pathology image should look like for this patient if this patient is another cancer subtype, MOV. In such case, If we want to generate something for doctor to take a look that is not happening, that doesn't exist, we use diffusion model to do that. So those kind of classification, we only do vision transformer, no diffusion. If we want to show something, we do diffusion.
Thank you.
Hi, thank you for the talk. A problem that we often encounter is that for foundation models or multi-domain, like multi-modality models, is that the data size is very imbalanced across the different data sets. Do you think this creates a bias in the model? And yeah, how do you usually deal with this?
So this is inevitable. The data set could be biased. Like for here, where lots of patients, most of our data are lung cancer patients, and most of our data here are lung cancer patients, and there are very few less patients from liver cancer. So the model will, as I mentioned, our model is better lung cancer, not liver cancer. The solution here is again to do a second stage fine tuning. If we really want to apply our model to liver cancer, we need to collect some other liver cancer patient data from somewhere else, and then fine-tune our model to that population. So this is how we address imbalance. We still train on everything, even if it's balance or imbalance, train everything. And then for the specific task that is not very well represented in this population, pre-treatment population, we try to collect more data and fine-tune on it. This can somehow mitigate the imbalance. And even if we don't have some other data, then we just train one model using all data, and then keep training the model only using liver data if we want to only do liver-related application. So this can make the model shifted to liver population and do well in liver. This is how we do it.
Okay, thank you.
Okay, I think we'll go to Slido, and Patrick will lead our Slido relations.
I'll try my best. Okay, first up, as an engineer with experience in CT MRI analysis, what would you recommend for expanding into broader medical AI foundation models? That's part one. And then part two, are there specific open source projects or public data sets that could help bridge from traditional medical imaging to these newer multimodal approaches?
So I don't quite understand the first question, like how to expand their expertise from MRI CT to general medical imaging. If they are asking for like software AI framework, which is actually related to the second question. So, this is from what we observe. In AI, there's always a trade-off between, there's always a trade-off or development of data and the model. If we have lots of data, we collect more and more data, then our current model, like deep learning model, is not strong enough to model all the data. We need to develop a new model like generative AI. If we have a new model like generative AI, which works very well for all the existing data, then people start to focus on creating new data sets, like ImageNet, this kind of very pioneer work. I think at this stage in generative AI for medicine, the model, the method model is actually very good. What we are lacking now is the data. The model is very standardized. For all the 2D image, we always use Dino V2, something called Dino V2, which is state-of-the-art on different kind of medical imaging, MRI, CT, pathology. We found that Dino V2 works very well. On 3D image, we tried many different methods, and we found that 3D mask autoencoder always work very well. So there's not like a choice option of using what kind of method. We found that these two models work almost the best for AI in medicine, for medical images. The reason is that training foundation model is very time-consuming, often take 2 weeks to train such one model. Then we cannot do ablation study effectively, efficiently. So I don't know which part of techniques is useful because training once will take 14 days. I cannot do ablation to do it multiple times. So what we can do is just to follow what general domain did and use the model from general domain and do some simple adaptation to that. But if they want to start from AI in medicine, my suggestion is to follow the general trends in general domain, and there are some very standardized tool and method to do it.
Part of the question could be, for example, non-imaging areas of medicine that you see fertile, like lab. We have a lot of lab data, billions of measurements. Should we have a foundation, or do we have a foundation model for looking at laboratory data and then combining it with the image to perhaps get more power?
So there are some recent work in modeling that could be used for this kind of lab test. That's like modeling tabular data. It's like a table because that's a lab data. And even general domain showing that foundation model works well for table data. Table data is still very challenging because the pattern there could be very simple. It could be a simple regression, linear regression. So that's why I think generative AI is still limited in modeling lab test tabular data. And if we have lab tests in some application we simply concatenate the lab value to the image embedding to make it a longer embedding vector. But the most powerful thing is still to model text and image.
Another one from Slido. Could you please share your thoughts on, one, bias in the foundation models due to lack of enough data from some demographic groups, and two, uncertainty quantification in terms of figuring out regions where the model may not be reliable?
Yeah, this is a very good question. So we don't have a concrete example for showing the foundation model trained on certain population do not do well on another population. There's some previous work, right, in AI, not in general AI, people showing that that's a Nature Genetics paper, people showing that GWAS study or other study down on this kind of population cannot be shifted to another race. But in general AI, it's a little hard to do it because for example, for this kind of data population, we would expect the model will not do well on liver and do well on lung. But actually, it's not strictly correlated with the number of data points. Because those data points, its contribution is not only related to its quantity, number of patients, it's also related to its quality. And they have lots of internal similarity, like some cancer type is similar to some other cancer type. So this is a very hard problem, how to quantify the value of each data point. The best thing we can do is, again, to do some fine-tuning and based on the performance on the second stage of fine-tuning to know what the model may not do well. That's why we are trying to show the generalization to new population, new cancer center. Use those kind of data to help us understand the population we cannot do well.
Did we hit the second question there? It was a two-part question.
Yeah, that's a very good problem. So we actually, that's a very important problem in medicine. In addition to knowing the label, which cancer subtype, we want to know the confidence, whether the model is confident or not. This can be solved by traditional AI methods showing some confidence. But what we did, actually, another thing we did, also similar to our mixture of experts model, for a given patient, if we want to predict cancer subtypes, I will ask this patient, use all three different foundation models, train a different population to predict the label for this patient. And they show a good agreement among those three models, then we are confident the model is make good prediction. If those three models, they are all very confident by themselves, but their prediction do not agree with each other, then we know it's not a very confident prediction. So we are actually using multiple foundation models, training from different populations to help us measure the uncertainty. And that's why this kind of world model have the kind of ability to give us not only prediction, but also confidence and uncertainty.
Is that our Slido? Great. Yes.
Maybe I missed it, but can you talk about the explainability aspect of the AI's determination of the result? Does it indicate, oh, I picked this because of this feature in the image or whatever?
Yeah, first of all, doing explainable AI or interpretation for GenAI is still a very challenging problem because GenAI has so many parameters, such a large search space. It's very hard to find which features the model used to make prediction. So best thing we did is to generate this kind of saliency map where the model, both our model predict this patient as an AMD patient, macular degeneration, and then we just highlight features, the pixels, every pixel is like a feature, highlight pixels that the model used to make the prediction. And those kind of pixels will be the interpretation we provide. We tell the doctor where they should take a closer look. They should take a closer look around those kind of regions with red pixel. This is what we did. Again, this is just using general domain method. We didn't develop a new method for GenAI. That's still a very challenging problem.
If I could add to that too, which, as you've noticed, that's what I like to do. What about for the text embedding explanation? So you showed that picture that we were looking at before, where you have all the red dots. Is there an opportunity there, since it's text? It seems like there's a great opportunity to make it very understandable. But Do we have data or experiments in that area?
Yeah, this is what we are doing right now using text to do interpretation. So in the previous salience map, I showed the region pixels we should highlight. After we know where we should highlight, where we should focus on, we can go back to the text space, then generate a sentence there. The text space will generate a sentence telling us, okay, those are retinal region with what kind of shape, what kind of things. So we can also generate text. This is what we are working on now to describe those parts we highlight. But we found this is it's very challenging to generate the fine-grained text description. It's very limited, very challenging question. And if we are actually using diffusion model, like I introduced previously, to do this, to generate text. Once we have the text, interpret what we see there, we can generate another new image, a synthetic image, to showing that what if we change the condition? What if the patient is normal, not AMD patient? What this image looks like? So that's the generation part we are working on, but it's very challenging.
I just wanted to comment that I thought it was very entertaining that Esperanto turned out to be English. No comment, no answer necessary. If we have any other questions, otherwise, not seeing any hands up, I will please join me in thanking Sheng for a really fascinating seminar.